Well, I can use that. Let's set numbers in the calculator.
Has a bachelor's in nursing, and she like works for the women, she's a math brain.
Literally have to just like jump in the deep end.
Okay. Yeah, my calculator.
You guys, for the first part of this problem, it's not required that you have the data in order, but it's always a good idea to sort your data, this kind of problem. Especially because I'm always going to ask you a problem like part D. And it's a lot easier to count stuff if they're in order, right? So up here I've got the data, I sorted it in there. L2 should have been L1 minus 6.5, right?
Yes.
Thank you. And then L3 will be L2 squared. So hopefully those numbers look familiar. And then to add those up, I go to second stacked math, number 5 for sum. And I want to sum up L3. Alright. So let's shoot over to that.
Formula dude works better than third one.
Alright guys, I'm not going to fill this whole chart in. Hopefully those numbers look familiar. As I'm walking around, it looks like everybody's pretty much getting the same thing. Your sum came out to be, which is weird. Well, that's what we got, that's fine. And then here, hopefully, it kind of made sense about the n minus 1. There really is a lot more to that story. N minus 1 is going to pop up later this semester. We'll talk about it more then, and it's still not going to be the complete picture. Because to get a complete picture, you need at least calculus under your belt. And some of us have that, but not all of us. So I'm not going to go any more than what I already did. So the sum was 69 divided by 12 minus 1, 11. So it looked like most everybody got there. And the point I was trying to make is to write that down, it's fine to round. In general, you do not round anything until you are done. Right? So I still have more to do with this number. So do not take the square root of 6.27. So let me show you on the calculator. Well, let me do it here. Got my own little calculator. This really kick-ass button. Oh, it's so kick-ass. So if I do 69 divided by 11, I get 6.27272727. If I want to do the square root of that and not have to write all those damn decimal numbers down, I do the square root of the answer I just got. That's what the A and S button is. Second, negative to get the square root of answer. That is the best little memory key ever. That always holds in memory the last number that shows up. So I don't have to round at all. So then everybody should have gotten 2.505. Remember, I said round at least 3 places, and that takes care of most rounding errors, because we got to use the standard deviation to do other things. So let's say this will be 2.505. So what does this letter S stand for? Of a sample. I like it. Remember, it's not universally true, but the Greek letters mu and sigma are population. Our letters X bar and S are sample. I like it. So here's the weird thing. Let me ask you this question. All right. This part C is much more important than it looks like on this sheet. A real simple question. If I am at position 10 and I want to get to position 20, and every step I take is too big, is 2. You guys kind of with me? Mm-hmm. How many steps until I get to position 20?
5.
How'd you get that? How far do I have to go?
10.
20 minus 10 divided by how big each step is. How far I gotta go. The data point minus the mean. That's how I want to see how far away from the mean it is. The data point minus the mean is how far I gotta go. 20 minus 10 divided by how big each step is. Standard deviation. That's why I call standard deviation steps, because it's a nice visual. This is actually what we call the z-score. So if the standard deviation is the tick marks on the ruler, the z-score is what I find when I measure something with that ruler. So what do you guys get when you do that? Let's see, we get 9 minus 6.5. Because the data point's 9, and what letter represents the data points? X. So 9 minus 6.5 divided by 2.505, you should have gotten like 0.998. So that means that 9 is almost 1 step up from the mean. What if it was something below the mean? It's going to come out negative, that's all. It just means it's below the mean if you get a negative. So if your test score translates to a negative z-score, that means you scored below the average of the class. If your test score is a positive z-score, you got above the average. If your test score had a z-score of 0,
Means you have average.
you are on the average. You are the average. Goodbye. Right? All right. Yes.
Will the z-score always be visited?
You ready? Yes. And later this semester, you guys will think that I need medication. That z-score formula is going to look like it changes. There's going to be p's in there if I'm talking about percentages. There's going to be double x's and s's if I'm talking about 2 samples and I want to see how far apart 2 samples are. All kinds of weird shit. But it's always my data point minus the middle divided by the spread. That's what z-score always is. So we're going to have like multiple z-score formulas, and crazy ass Jeff says they're all the same formula.
They are.
They are. Thank you. Yes. And the more that makes sense, the easier time you would have in mathematics. Because mathematics is all about, these all look different, and the mathematician would say, they're all the same damn thing. And that's why the mathematician has an easier time with them, because they don't think that I have to memorize all these different things. All right, maybe. I'm not saying it. Anyway. I was just lucky that I look at things like that. This is a very important thing. We're going to talk more about this in a minute. So really what I'm doing here is, if the standard deviation is a measure of the average spread, then as I move around my data, if I go 1 step up and 1 step down, I'm curious about, well, how much data will I catch? Very often I'm going to catch a decent amount of data. Sometimes I'll catch nothing. Because I could have data that looks like this, and there's like nothing in the middle. A bunch of young people, a bunch of old people, and there's nobody in the middle. So if I go up 1 step, down 1 step, I don't catch anybody. So there's a lot of theories, we're going to talk about a couple of them today, about how much of the data is within 1 step, within 2 steps, within 3 steps. 3 steps? Where am I at? Let's see, so the mean was 6.5. If I go down, and again, just to remind you guys, there's a whole other side with all these problems worked out, as an example. If I go down 1 step, and every step is this big, right? If I go down 1 step, where do I end up?
3.996.
Something like that, right? And if I go up 1 step, become a 505. I'll end up where? I like it. So now I think of this as my fishing net. I'm throwing out a net. And how many data points do I catch? So obviously I don't catch anything below 4. I don't catch anything above 9. So which data values do I catch? I catch everything except 2 I don't catch, The 10s I don't catch. Anything else? Let me see. I think it's a 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you guys can't see what I'm doing. You guys should, I think most people got there. I catch 9 data values out of how many? 12, and that is 75%. So for this set of data, 75% of the data values are within 1 step away. Cool, I like it. So let's do this. Oh yes.
Where should you get a number and not 3.9 and 5 just looking for?
You would still include the 4, yeah. But that almost would never happen. And that's why I say standard deviation go out 3 places so you can really see which side it falls on. You see what I mean? Yeah.
I was going to say, would ESPN make 2 and 2 outliers?
Oh, the idea of outlier, we have to make more technically something that we can analyze. And the funny thing about outliers is it totally depends on how far away is far away enough for you. Right? So it could be very different. And again, it's related to like, if I have a normal operating area for a nuclear power plant, I'm going to define unusual. I'm going to define my outliers. I don't have to go very far away, right? I mean, the minute that needle goes a little bit up in the green towards the yellow, I'm getting out of my freaking chair, and I'm like, what's going on? I don't want Godzilla shit. Right? Does that make sense? Or if I'm somewhere where it doesn't really matter that it's very far, then my tolerance could get bigger. So the idea of outlier is kind of vague. There are multiple ways to consider what outliers are. I like it. Okay. And the first kind of rule we're going to use is to go up and down 2 standard deviations. And we'll see why here later today. Yes?
Why when you're subtracting the IPR about the median, you multiply that by 5?
So that is one method to determine outliers for a box plot. In fact, that's a method that's used to be more conservative, to have more outliers than you would for some other methods. And normally what you do, when you find something that you think is an outlier, what would you do with it? So if you're measuring people's blood pressure, and there's one person that is really far away from the other people, you're going to go see what's going on with them, right? So do you want to be more conservative or less? Do you want to have more outliers and go find out that they're fine, that it just runs in the family or whatever? I'd rather have more outliers so I can go talk to those people individually. So there are multiple kind of ways for box plots to find outliers. And the way that I like to use is more conservative.
So then, if you pick 1.5, you're just being more generous. That's all it is.
Well, it's based off of normal distributions and percentages inside of them and trying to translate that to, there's a lot behind it. So the specific value of 1.5 does have a place it comes from. We just don't know enough yet. I'm going to come back to it later this semester. We don't know enough yet to go back and really analyze why that would have been picked. Because they actually call 1.5, what do you call it? Slight outliers. And if you go out beyond 3, they call those extreme outliers. So it's, okay, I like it. Maybe. Okay, so let me think. How much? Let's do this. Let's just do a little bit more. We'll take a break. And then when you come back, we'll do the practice test. Let me make sure where they have this for you. I want to show you this picture. Where are you? Oh, that's right. This book doesn't do it till later. Damn. Yeah, this book doesn't do it till later. That's right. All right, sorry. I always forget. Give me 1 second. Or maybe several seconds. There it is. 414, 342. Oh wow, not till then. Shit. Okay. I wanted to talk about, I'm going to wait for this because they put this later. It's the idea of whatever the distribution looks like. Can I say if I go out one step, if I go out two steps, is there some definite amount of the data that I'm going to catch? And there is, actually. It's kind of neat. It's called Chebyshev's theorem for any distribution. So we're going to talk about that later. It won't be on this test yet. But I do want to formalize this. This is the z-score formula. So if I ask you to find a z-score, this is the formula that you will use. So let's do this. Let's take a break. When you come back, the first thing we'll do is create a formula sheet that you'll be able to use on the test. And then I'll give you guys the practice test for you guys to start trying today. Cool. All right, so come back at 11.